Morning, it is June 24th. You guys are just coming off your first exam, and you guys did pretty good. As you can see, we go up here to the statistics. You guys, after it loads, did pretty good. Bell curve is way over here in the 80s, 90s, and 100s. So pretty good. There was one question where the answer was wrong. Not the answer, but the thing was on the wrong answer. So I moved it, and that got a lot of you guys that had 29s up to 30. So, so yeah, good test. Good job, everybody. So let's just get started on talking about Module 4. So as you can see, I uploaded everything, chapter 4, 5, and 6, or unit 2. I uploaded everything. I was hoping Citrus would have their class up already before I did this, but they didn't. So here it is. There's everything. You got PowerPoints, you got the worksheets to work through, and you have a lot of videos and some helpful websites. And then from now on, we're going to be using the periodic table. So you're going to want to have a periodic table on hand. So what I have done is I have provided with you a periodic table. This one's nice, color-coded, has all the functional or the different types of atoms on the periodic table. Things like alkali metals and whatnot, which will be the subject of chapter 6. So you want to be able to reference that a little bit, so you can like open it up in another tab, or you can print it out. It's colored, so I don't recommend that. It's up to you though. But that is there for you. And so everything is here now. I posted the chapter 4 quiz for the attendance today. Yesterday's attendance was taken by the exam. You all took it, so everybody has attendance for the first 3 days so far. So yeah, you can click on that quiz anytime for today, and that will be your attendance and your chapter 4 stuff. So before we go into the atomic history PowerPoint, which is what we're going to talk about today, are there any questions on the exam? No? Oh, is it not? Okay, that's talking. Okay. Well, let's just get right into it then. All the exams were to be graded on the spot. My scores are hidden. It showed it to you right then. Huh. Well, let's see what we can do. Let me see if I can do it over here. All right. Boop, boop, boop. Grades. Can you see your grades right now, guys? Oh, okay. There we go. Boop. How's that? There was a button I needed to click. So I just clicked it when it said automatically post grades. So you should be able to see your stuff now. after it updates. There was an option that I didn't see in Canvas. Weird. Try that again. Okay. Assignments will be busted. I updated it. Huh. It says that it's muted. Weird. All right, well, we'll play with that because all of your grades so far have been posted for your quizzes and whatnot, and then your exam. So I don't know why it would be muted. Yeah, grade posting. Hidden by default, any grades that are already posted are visible. Choosing both grades. Okay. Student view. Grades. Okay, should pop up now. When I clicked on student view, it showed up. Is it just showing you guys nothing? Is that what's going on here? Waiting to be graded. Doesn't show. Still doesn't show. Awesome Canvas. I'm live. Huh. Okay, well, I'll play with that. For some reason, it's saying, okay, I see what it is. Okay. This is really silly. I got it now, kids. It'll update now. It's really silly. Here you go. And then this would be post. Now you should see everything. All right. All right. Anyway, I just posted them. You should be able to pop it up. There you go. All right. Let's get on with it then. Let's get right into atomic history. So in the previous unit, we were just kind of talking about some basic ideas of matter, and we got into some classifications of matter versus mixtures versus compounds versus elements. So back in the day, they didn't really understand elements. So to talk about the atom and what it's made of and how that relates to the rest of these this class, We're going to get into a little bit of the history of them, how we discovered each little bit, and then we'll talk about protons, neutrons, electrons, atomic numbers, ions, isotopes, that kind of stuff, all the chapter 4 stuff. And then that will be the end of the meeting. And then you guys can go ahead and work through the worksheets and take the quiz, or you can just straight up take the quiz. It's up to you. So let's get right into it. So anyway, back in the day, a long time ago, you had over 2,000 years ago, they didn't really do experiments. They did what's called thought experiments, and they used logic to kind of answer difficult questions. And so what was everything made out of was a big key question. And so they used a practical way of doing it. If you picked up mud and you squeezed it, water came out. So that means there must be an element called water and an element called earth. And then when you mix them together, you get mud. And then when you look at people, you know, they have blood, so they have water in them. They're also solid, so they have earth in them. And then they breathe air, so they have air in them. And so for the longest time, everyone thought that there was earth, wind, fire, water, air, and something called the ether, or the spirit, basically. However, Leucippus and Democritus had a very good thought experiment, but because Plato and Aristotle kind of come after them, their thought experiment gets thrown away. And what is it? Well, Democritus has this question. He said, okay, yeah, sure, you know, cheese might be earth and water too, but what happens if you cut cheese in half? Well, it's still cheese. It's just two smaller pieces. And so if you just keep cutting the cheese in half, there eventually will be a piece of cheese that you can't cut. And the word atomus means uncuttable. And so that's where the word atom comes from. So Democritus's thought experiment was to say, what is the fundamental smallest piece of cheese that you can no longer cut with a knife? And that is what the cheese is made out of. There's some fundamental tiny cheese piece. That seems silly to people 2,000 years ago. So of course, when they died, Aristotle comes in and argues for earth, wind, fire, and water. So that's basically the theory of what everything is made out of for 1,700 years or more until the scientific revolution. And people started doing experiments with matter and mass and looking at how things changed over time. And basically what they found was that matter was made up of elementary particles. That's where the word element comes from. But that the elements weren't just earth, wind, fire, and water. There must have been something else besides just those elements. And especially when they were able to do experiments with electricity, they found out that you could take things like water, which was always considered one to be one of the fundamental elements, and if you passed electricity through it, you could get it to split into two gases. So they were starting to understand that there must be something else going on. So the father of chemistry is a guy by the name of Lavoisier during the French Revolution. He was the one who kind of basically put forth the scientific method. Him and Boyle in the 1600s kind of developed this system. And through his work with mass, the law of conservation of mass, he was able to come up with a basic idea of what was elements. John Dalton in the 1800s is the guy who's going to come up with the very first atomic theory. And he's going to call elements atoms. He said that when you have something in its purest state, you have it in its undivisible state, meaning it's the smallest piece of that pure substance that still has the properties of that substance. So the idea behind Democritus's theory was that if you cut up the cheese, eventually you'd have a tiny piece of cheese that could no longer be cut and have it still be cheese. And that's the idea behind Dalton's atomic theory. The atom, according to Dalton, was the smallest piece of something that was still that thing. So if you had a piece of gold, you could chop the piece of gold down until eventually you would have one atom of gold. He said that all atoms were exactly the same, and that what made atoms of a particular element were all exactly the same. We know that is different now. They're different very slightly. And then he said this, what we see as compounds and chemical reactions was just these atoms rearranging themselves into different groups. And again, water was a big clue for this. Water, when you split it using electricity, would always split into 2 parts hydrogen and 1 part oxygen, which was called the law of definite proportions. So this is Dalton's atomic theory. He said that the matter wasn't getting destroyed, it was simply rearranging. Now, later on, we invented atomic weapons and figured out how to destroy matter, or at least convert it to energy. But at the time, this was a revolutionary idea. Many people didn't even believe air was made of things at the time. So just a little quicker refresher on the idea of charge. Charge is very similar to magnets, where you have a north and south end of a magnet. In charge, we give it a positive and a negative symbol. Now, what it just means is that they're opposites of each other, and the nature tries to put these two things together to become neutral. So when it comes to similar charged particles, they repel each other because, again, there's no energy incentive for them to get together to become zero. So they repel. So like charges repel. And then opposites attract is energetically favorable because when they come together, they are calmer at the zero charge. That's going to be important because charge is going to be discovered with atoms. So for the longest time, we have the model of the atom as just a tiny ball, basically, that is uncuttable. It is the absolutely smallest thing in the universe. Until we get the invention of the cathode ray tube. The cathode ray tube is really cool. It's basically an empty tube, meaning there is nothing in there except for those pieces of metal electrodes. It's a vacuum, okay? So when we were getting electricity, one of the things that people wanted to do is they just wanted to electrify everything. And I'm sure at this point you might have read Mary Shelley's Frankenstein, but that's a good example of one of the very first science fiction novels, because it's the idea of like, oh, look what we can do with electricity. We can even reanimate flesh. Well, one person had a question. What if we electrify nothing? What will happen? And so they expected nothing to happen, but what was crazy was a green beam of light would go from one electrode to the other. And the electrode would move from the cathode to the anode, and that's why it was called a cathode ray, because it would shoot from the cathode to the anode every single time, and it gave off this really eerie green light. This was very popular amongst people. It was very popular with people who like to conduct seances. And basically, they thought they were opening a portal to the underworld so that you could talk to your dead relatives. Not the case. So a guy named J.J. Thomson comes in, and he goes, oh, well, it must be charged then. There must be something that has a charge to it, because there's nothing in that tube. So when we pass electricity through it, we must be generating these pieces. And I suspect, because they're moving towards the positive end, that they must be a negative particle because they're attracted to the positive side. So what he does is he takes an electromagnet and he puts it around the tube. And what he finds is that the beam of light is bent up towards the positive end of the electromagnet. So this means that basically inside those disks, there must be in the atoms a negatively charged particle that is set free when electricity is passed through it. And so because he used electricity to find this, he called it the electron. So nowadays we don't use these types of TVs anymore. Maybe your projector in your classroom has this, but a CRT television is actually called a cathode ray tube television. And the way it works is you have a cathode ray and it shoots the beam of electrons. And then on the other end is, on this end is a film that is painted with a substance that glows when it's hit with the electron beam. And then this magnet over here is hooked up to some sort of electronics, and it slowly passes the signal across the screen, and that makes the image. We don't use these anymore because LCDs are cheaper and easier to make. Also, these were heavy, full of mercury, so nasty stuff. So J.J. Thomson came up with a new model of the atom. Instead of a ball, they were now this loose amalgamation of some positive stuff and negative little balls that he called the electron. He called it the plum pudding model because back in the day, plum pudding was popular. You can think of it like blueberry muffin nowadays, like the blueberry muffin model. An atom is a blueberry muffin where the positive stuff is the muffin and the negative things are the blueberries, however you want to think about it. So this was revolutionary. There was stuff inside the atoms. Atoms, the uncuttable thing, turns out you can get inside of them. So Millikan comes in and he wants to study the electrons. And so what he's going to do is he's going to try to figure out how much they weigh. And so he devises this really cool experiment. Oh, it's not going to load. Here we go. He devises this really cool experiment where he has a chamber and he's going to squirt some oil in there, and he's going to hit it with some radiation. So at this time, radiation is discovered. You might have heard of someone called Madame Curie, Henry Becquerel, these guys. And so basically they find with strong enough radiation, you can ionize, or you can basically split the electrons off of atoms. So what Millikan does is he creates this chamber, and he has two charged plates, positively charged plate and a negatively charged plate. And when he sprays the oil, a small amount of the oil will go through and be ionized, so its electrons will be stripped from the oil, and those electrons will then go up and stick to the positive plate, and all the negatively charged oil now will go down and sink to the bottom of the plates. So he could conduct this experiment, and then afterwards he could weigh the plates. He would have had the mass of the plates before, he has the mass of the plates after, and he could see what the mass was added to each plate. So the positively charged plate would be the mass of the electrons, and the negatively charged plate would be the mass of the positive stuff. Now, the reason why a lot of these experiments are so popular, and we're talking about them, is that how easily they were replicated. Anyone could make Millikan's experiment and reproduce it. So when he got extraordinary results that would normally be passed off of obviously you can get nothing, everyone could repeat this experiment and get this same number, so they knew they must have had a good result. And what they found was that electrons were basically massless. As you can see, 9.1 times 10 to the negative 28 grams. That is basically nothing at the time. It was almost very hard to detect. You had to use a very large amount to actually be able to detect the difference. That was one of the big things that drove the scientific revolution, was better things like better equipment, like better scales, so you can actually determine these tiny numbers. So at that point, they knew electrons were negative. They knew they were in the atom. and they knew they contributed almost nothing to the mass. So the question was, what the heck is this positive stuff? Well, for the longest time, they didn't really have a tool. They didn't really have good tools to understand atoms, but then better scales were made, and they did a bunch of cool experiments with mass, and they were able to discover better elements. Well, then we got electricity, and so using that tool, we were able to discover electrons. And now we discover radioactivity, and it's time to be able to have a good tool to understand the positive stuff in the atom. So Henry Becquerel is a really funny story. He basically discovers radioactivity by accident. He was studying these uranium ore rocks because they were, isolating new elements. And he wanted to go on vacation, as you do, because there was no air conditioning. So when it got hot in the summer, you tended to just go away for a couple months. And he decides to leave, so he takes all these rocks he's studying and he just throws them in a drawer. He doesn't even think about it. And inside that drawer was a bunch of photo paper. So back in the day, they used to have to make photos where they would develop them in different solutions. He comes back from vacation. He opens the drawer so he can resume his study of these rocks. And guess what? The rocks have taken pictures of themselves on the paper. So he says there must be some light that we could see or something coming off of these rocks. Madame Curie is influential in isolating and making these uranium ores into their individual different elements. And so she discovers radium and radon and polonium. And then the guy we're going to talk to next, Rutherford, he's able to split the different types of radiation into their different parts. And what he finds is that radiation, majority of the time, consists of 3 different types: a positively charged thing, a negatively charged thing, and some energy light called gamma rays. And of course, he just called them alpha, beta, gamma, because first, second, and third thing he found. So why is this so exciting? What's the big deal? Is because now with the alpha particle, we have a piece of the positive stuff. And so Rutherford decides he's going to do an experiment where he's going to take a piece of this positive stuff and he's going to just shoot it at a very dense atom to see what happens. Now, according to the plum pudding model, here's Rutherford's experiment. You have the alpha particle source in here, and it's coming out of a tiny hole, so it's going to go straight. And he's shooting it here at the gold foil. And then we have a photo paper all around it, so we can see where those alpha particles go. Now, if we were looking at the plum pudding model, we should expect to have the beam of light go straight through, or the beam of alpha particles go straight through. Because they're positive, the plum pudding model suggests that the positive was just this loosely affiliated positive stuff. So when you shoot a high-powered bullet at a piece of tissue paper, it should just pass right through it because there's no force there to stop it. The picture of that explanation. So what happened is when he shot it, a very large majority of the alpha particles went straight through, but some of them were bent. And an even smaller fraction were actually deflected by the foil. They bounced off. He wrote in his paper, imagine you took a cannon and shot it at a piece of tissue paper and the cannonball bounced back and hit you. That's how crazy this result was. But again, this was an extremely simple experiment. So he publishes results and tons of people jump on and start reproducing the results. And not only do they see the exact same, but they also notice the exact same ratios. So Rutherford explains what's happening by saying that an atom is mostly empty space. Outside of this small dense center, which he calls the nucleus, are the electrons. And at the center of the atom is an extremely dense ball containing all of the positive stuff. And that what an alpha particle is it must be one of these pieces of nucleus without any of its electrons on it. Turns out that is right. Alpha particles are actually helium nucleuses. They just don't have their electrons. So he comes up with a new theory of the atom, that there is electrons outside of the atom. Early models suggested that they orbited the nucleus, but we now know that's not true. And that the nucleus must be this extremely dense center of atom at the center. And of course, electrons are negative. So what should the positive stuff be? Well, it's called protons. He comes up with this model of the atom. Now, through years of study, we have got to learn a lot more about the atom. One thing that we've also learned is that there is not just protons inside the nucleus. There are also neutrons. This neutron was discovered by a guy named Chadwick, who was a research fellow of Rutherford, and he conducted a similar experiment. But what he noticed is that when you took something higher, let's say larger than hydrogen, and you passed it through his experiment, the charged particles would be attracted, but then there was still a massive particle that would move that was not affected by charge. It was a neutral particle with mass. And so he discovered the neutron. And I just want to give you perspective. The neutron is discovered by Chadwick in 1931. Neutrons are going to be the key to taking things like uranium and turning them into nuclear weapons. And that program is started in 1939. So and that's because the theories behind it are out by 1936. So 5 years between the discovery of the neutron, they're already starting to talk about how to split atoms. And by 1945, we've done it. So 14 years from the discovery of this stuff to turning it into nuclear weapons. Pretty crazy. So nowadays, the modern atomic theory is that, yes, inside the nucleus are the protons and the neutrons. Protons are positive and neutrons are neutral. And then outside of the nucleus is this cloud of electrons. Now, we call it a cloud nowadays because they don't orbit. They don't tend to move in one particular direction. They tend to be in these different shaped shells around the nucleus. And so we call them an electron cloud. You can think of it like a fan. When you turn a fan off, it has 3 blades. You can see them. But when you turn the fan on, you can see this kind of nebulously shaped circle that you know is made of those fan blades, but you can't really tell where they are at any given moment. So that is the structure of the atom. Protons, neutrons, electrons. And protons and neutrons are inside the nucleus, and electrons are outside the nucleus in what's called the electron cloud. So let's just look at their symbols real quick. So anyway, we have electrons. They have the symbol E minus, and they are -1 in their charge, and they weigh 0 AMU. Now, what is an AMU? An AMU is an atomic mass unit, and it's an actual mass. It's just extremely small. It's 1.6 times 10 to the -24th grams. So rather than write that number out for all this kind of stuff. They just shortened it to just AMU. So when you say 0 AMU, you're saying you don't have at least this much mass. To be accurate with AMU, though, they actually have a mass of 1/1840 AMU, which is essentially 0. And they're found in the cloud. Protons have the symbol P in their plus. They have a charge of +1. They are found in the nucleus. And they are 1 AMU, or 1840/1840 AMU. And that means a proton weighs this much. The 18, or the 1.6 times 10 to the negative 24. Neutrons, also found in the nucleus. They have N with a 0, and they have no charge, and they weigh 1 AMU, and they're found in the nucleus. But if we want to be accurate with their mass, they're actually 1841 out of 1840 AMU. They're slightly heavier, ever so slightly. So before we knew about protons, neutrons, electrons, we used to talk about an atom in terms of what we call its atomic mass. So let me use the symbols they use, A and Z. Okay. So there's A up here, there's Z down here. And right here, A is, we would write the atomic mass, or the mass, atomic weight, or the molecular mass, things like that. Atomic mass. And for atoms, because before we knew about protons and neutrons, when we would find their individual mass units, the atomic mass would be how we would find them. And carbon has atomic mass of 12. But if you look on the periodic table, you'll notice it says 12.001 and all that kind of stuff. And we'll talk about why it says that in a second. But what we found out is what the atomic mass actually equals is the protons plus the neutrons. And that this number down here, Z, which is the atomic number, is the protons. And while Dalton said that atoms were the smallest thing, it turns out that they have these little particles inside them. And which is the most important of those particles? It turns out it is the proton. The number of protons identifies the atom. So when it comes to carbon, carbon must have 6 protons. If it doesn't have 6 protons, say for instance it has 7, well, that's nitrogen. And if it has 1 fewer, well, that's boron. So the number of protons identifies which atom it is. So in the case of this carbon, if our atomic number is 12 and the protons is 6, then the neutrons have to be 6. So when you're looking at a problem and it asks you like how many neutrons something has or how many protons something has, you can look on the periodic table. And the little whole number there, in this case, it's on the top here, right there. You can see, well, here, I'll use the cursor since my thing doesn't want to work. You can see that guy right there. That is the atomic number. That is a 1. And you'll notice that the mass down here is not a whole number. And that's because on the periodic table, we use average atomic masses. Because as it turns out, Dalton was incorrect when he said that all atoms are the same. If we have a carbon atom, carbon can actually exist as 3 different atoms. Now, they're not all equal. Some are more abundant than others. But there are actually 3 different types of carbon atoms: carbon 12, carbon 13, and carbon 14. These guys are all called isotopes. And they're the same element, so they're all carbon. But you'll notice, because of their different atomic masses, their neutrons are all different. So their protons are going to all be the same. They're all going to be 6. But the neutrons here are going to be 12 minus 6, 6, 13 minus 6, 7, and 14 minus 6, 8. So they have different numbers of neutrons. So these are called the isotopes of carbon. Carbon 12, carbon 13, and carbon 14. Now, if we go back to our periodic table and we look at carbon right there, you'll notice that carbon says that its atomic mass, in this case it's called its average atomic mass, or mass number, is 12.011. And that's because it's an average of all of the atoms of each type of isotope. Well, as you can imagine, if it's an average of 12, 13, and 14, and the average is 12, that the vast majority of atoms must be carbon 12. And that is true. When it comes to abundances of these, this is basically 99%, and this one is approximately 1%, and this one is extremely small, 0.1%, depending on the situation. So that's why these numbers are decimals. Now, some things have a very large abundance of one particular isotope, and that's why their number is so close to being rounded to a whole number, like, for instance, 12 and 14, 16, 19 for carbon, nitrogen, oxygen, and fluorine. Same thing with hydrogen. Vast majority of hydrogen is hydrogen 1, but there is some hydrogen 2, and there is some hydrogen 3. Helium, same way. Vast majority of helium is helium 2, but there's also helium 4. There's also helium 3, and there's helium 2, but that's super rare. Anyway, those are the numbers that you see on the periodic table. The big letter here, that is your atomic symbol, and it is a capital letter. You need to have at least one capital letter to have a chemical symbol, and you'll have one lowercase letter if you needed another letter. So for instance, when we're talking about boron, well, boron is B, but we also have beryllium, so we can't just use B again, so they used BE. Now, most of these symbols make a lot of sense, but a lot of these names are very, very old, so they have weird symbols compared to their names. Potassium here is K, even though we have potassium there, and that's because it used to be called something called carum. And then we have silver, auger, and we have gold, aurum, and so that's why their symbols are different than their names. Lead is a good example of this. We still use this word. You ever gotten a problem with your plumbing, you'll order a plumber because they used to use lead, and lead was called plumbus or plumbic, that kind of thing. And then, of course, you have sodium, which is Na because it was called natrium. And so there's a bunch of other stuff. Tungsten is W because it used to be called Wolfstrom. So interesting stuff. And I like this one because it actually has all the elements up here updated. We actually have synthesized all of these elements down here. So those are isotopes. Same number of protons, but different number of neutrons. That makes them the same atom, but it changes their mass. When we look at the mass number on the periodic table, that's going to be the average of all the atomic masses put together. So only one more thing to talk about before we move on, ions. When it comes to the world as you see it, very few elements are actually existing in their elemental form. Many of them are going to lose electrons or gain electrons to make themselves happy. So a good example of this is sodium. Sodium is normally 23 and I believe it's 11, which means that its protons are 11 and its neutrons are 12. And its electrons, if it's neutral, well, if it's neutral and we write the charge up here, then that would mean that the protons have to equal the electrons, because charge is equal to protons plus electrons charge. So in this case, our protons are 11. Our electrons have to then be negative 11. So we have 11 right here. And so that equals 0. But sodium hates being a neutral atom. What it likes to do is it likes to kick off its electron. It's still going to be 23. It's still going to be 11, but it's going to lose its electron and become the positive ion called sodium ion. Positive ions don't really change their name. Negative ones do. They go from their enes to their ides most of the time. So instead of chlorine, you get chloride. So notice our protons are staying the same. Protons always have to stay the same. Our neutrons are staying the same. But now our electrons are 10. And that's because we ditched out an electron here. So atoms that are usually made of metal like to lose their electrons. They like to give them up to other people. That's why they're such good conductors of electricity. And things that are not metals usually like to gain those electrons. So we mentioned chlorine earlier, and if you're like me and you like salt, you know sodium chloride. Chlorine tends to be 36 or 37. It is number 17 on the periodic table, if you look over here. And so when it becomes an ion, it likes to gain electrons. So it wants to get an electron, and we get the chlorine -1 ion. It's still going to be 36, still going to be 17, but it gained that electron, and it becomes the ion chloride. So that's atomic structure in a nutshell. Everything from atoms being tiny balls to protons, neutrons, electrons, to isotopes and ions. And that covers just about everything in chapter 4. So today's quiz is up. You can go to the module and you can take it whenever. It is a quiz again, so you can take it a couple times if you want until you get all the answers right. The worksheets are up, so you can work on those. Remember, you don't need to turn those in. Those are just there to help you work through them. And I'm available for questions throughout the day. Remember the quiz, you can retake it, so don't feel pressured to, get everything. You can, miss a couple problems, kind of get the answer, and then, still get a decent grade on it. But then tomorrow when we have our classroom session, we'll have a little time where we're going to do questions on chapter 4 before we move on to the chapter 5 stuff. And the way that the week work looks, we're going to do chapter 4, and then we're going to do chapter 5, and then we're going to do chapter 6. So we're not going to have another quiz or another exam this week. That we'll do on Monday. All right, I'm going to stop the recording there.